There are never really any topics that we leave behind in calculus. We've already seen that limits have popped back up when we talked about L'Hopital's rule, and now that we're kind of wrapped up talking about derivatives, we're ready to move on to integration, which is really the second major topic in calculus, the two big topics being derivatives and integrals. But as we discuss integrals, what we're going to see is that derivatives still play an important part in evaluating indefinite integrals, which we're looking at in this module, and definite integrals, which we will look at in module 10.2. So before we talk about indefinite integrals, let's talk about the idea of antiderivatives. And we'll even start a little much more basic than that. We're going to start with the idea of taking 3 and then multiplying that by 2. So if we took 3 times 2, that would give us 6. Now we want to divide that result by 2. So if we took 6 divided by 2, that would get us back to 3, which is where we started off. So similarly, we could start with 3 and square it. So 3 squared would give us 9. Now if we take that result and square root it, or take the square root of that result, then we would be taking the square root of 9, which is equal to 3, which gets us right back to where we started again. So multiplication and division. And exponents and radicals are both what we call inverse operations of each other. This may be a concept you've seen in some previous courses, depending on what you've covered, but these operations are inverses of each other, meaning that one operation will undo the other. So if we multiply by something and then divide by that same value, we end up right where we started off. If we raise something to the second power and then take the second root of it, we get right back to where we started off. So almost all mathematical operations have these inverse operations. Antiderivatives are simply the inverse operation for derivatives. So once we know how to take derivatives, we can figure out antiderivatives basically just by working those problems backwards. So another way to say that is some function capital F is an antiderivative of some function lowercase f if the derivative of capital F is equal to this function lowercase f of x. So for instance, we could say that capital F of x equals x cubed over 3 is an antiderivative of x squared. Because if we take the derivative of x cubed over 3, we get 3x squared over 3. 3 over 3 cancels, leaving us with just x squared. So we've been covering derivatives, starting with a function like this and working our way to our derivative. So now in this module, what we want to do is start with this final result and work our way backwards to the original function that would lead to that derivative. So we have one example of an antiderivative of x squared, but we could also say that capital F of x equal to x cubed over 3 plus, say, 6 is also an antiderivative of x squared, so of that same function, because if we take the derivative of x cubed over 3 plus 6, we'll get the derivative of x cubed over 3, which is just x squared, plus the derivative of 6, which is 0. So we get x squared as that final result. So what we're interested in doing is starting with this final result and working our way backwards to the original function. But what we can see here is that we can start off with x squared and then working our way back, get to two rather similar but different functions. And we could repeat that. We could keep going with this process. We could look at x cubed over 3 plus 12 plus the square root of 2 plus any constant that we want to add there. So what we can say is that every function has an infinite number of antiderivatives. So x cubed over 3 plus 1 plus 2 plus 3 plus 4 plus 5, I can keep changing this constant that I'm adding on. When I take the derivative, I'll always get to x squared. So what we do is represent the entire family of functions that are antiderivatives of f by writing capital F of x plus some constant c. So what we'll do is we'll start with x squared. We'll figure out some function that if we differentiated it would get us to x squared. So x cubed over 3 would give us x squared. So we could say the antiderivative of x squared is x cubed over 3. Since every time we take the derivative of x cubed over 3, we'll get back to x squared. And then plus some constant c. And that can again be any real number. As long as it's a constant, the derivative of that function will get us to x squared.